Hi, we're going to be doing another filter circuit. For this one, we're going to figure out what type of filter it is by inspection, find its transfer function, find what the gain limits to at high and low frequencies, and then find which frequencies maximize and minimize gain, and then the 3 dB frequency or frequencies if there's more than one. So this particular filter, we can think of it as a voltage divider again. So you've got this impedance divided by this impedance plus this impedance, and an L and a C in series has the characteristic that it's going to be infinite impedance at either extreme of frequency, at low impedance or high impedance. At low impedance, infinite impedance, it's infinite because of the capacitance, whereas at high frequency, so that's at low frequency, infinite impedance because of the capacitance, and at high frequency, infinite because of the inductance. Now, somewhere in between, these two are going to balance in series, and that, unlike in parallel where it adds to infinity, is going to add to 0 in series. So that means we've got 0 for one branch of our voltage divider, and we're going to have no output. So at the extremes, we are going to pass signal from the input to the output, but at somewhere in the middle, at the notch frequency, the resonant frequency, we're going to have no output at all. So this is a notch filter. So now let's go ahead and find the transfer function. And as before, we're going to say that H ends up being from a voltage divider, the parallel impedance at the bottom branch over the impedance at the top branch plus that. So in this case, plus R4. And adding up all of the different impedances in parallel there, we're going to have the effect of R3 and R1 together is a 50 ohm in parallel with J omega times 0.1 Henry plus 1 over J omega times 1 microfarad. Yeah. And we'll have this thing. Since that is going to show up twice, we may as well just divide by, actually, I guess I'll still write it in there, like that. Plus R4, 1 kilo ohm. Okay. And then, when we combine these two together, that'll give us 1 plus this thing over the sum of the inverses of this. So well, hold on. We would have been dividing by this impedance, and that means we would have 1 over 50 plus 1 over this thing. So we're just going to end up multiplying by 1 over 50 ohm plus 1 over those two in series, J omega 0.1 Henry plus, or maybe minus, J times 1 over omega 1 microfarad. Okay, so let's see then. We could take the 1K through, 1 kilo ohm over 50, and that's a 1K up there as well. And let's see, 1 divided by 100 would be 10, so 1 divided by 50 would be 20. And then over here, there's a J in both terms, so we can factor that out in front. We might consider multiplying numerator and denominator by omega here to get rid of the fraction in fractions. And we're going to have omega squared minus 1. And then the 1 over 1 microfarad is going to be 1e6. And let's check. So this is rads per second multiplied by henries. Then we've got and farads should end up being the same units, but then without the rad per second showing up there. So this would be, this should kind of be seconds squared. Yeah, so if this is henries per second squared, then this also has to be henries per second squared. So what we could do is just adopt the, if the units end up getting in the way a little bit, we could just for now say per farad. But if the units are getting in the way a little bit, then we could say, well, you know, everything is going to be in rads per second, and then not bother to write them. So let's see. We've got then the divided by j here can end up being negative j for that. And this is going to end up being 21. Okay, so if we want, we can take that thing and put it into both of those different terms too. Okay, so there is our transfer function. And looking at this thing, we expect something that goes to 0 when we're at the resonant frequency. And sure enough, if we have this frequency somewhere in the middle that's going to cancel out this term, which came from the inductor and the capacitor in series, then we're going to get 0 in the numerator, but not 0 in the denominator. Whereas at either extreme of frequency, this term will dominate what's going on in this term. So we are going to have a non-zero gain, but because we've got a 1K divided with a 50 ohm, we do have a gain that's kind of low there anyway. We have 1/21 as the limiting gain, which is what you would get for that voltage divider when this gives you infinite impedance. So that's confirmation of the transfer function and what the gain limits to at low and high frequencies. We can write that out. Low frequency gain, 1/21 equals high frequency gain. Minimum gain is 0 at omega equals 1/√LC, which would be 1/. Well, this is actually the same inductor and capacitor that we've been using for a while. So we could substitute in the numbers again, and they should look kind of familiar. And if we take 1/that, yeah, 3163 rad per second, which is going to be 503 hertz. Okay. So the next thing is to find the critical frequencies, and for that we're going to look for what the magnitude of H is. So magnitude of H at the 3 dB frequencies is going to be 1/√2 of the max magnitude of H, which in this case is 1/√2 of 1/21. So first let's find out what the magnitude of H is. So we might consider rewriting this a little bit into a bit of an easier form so that it's somewhat easier to read. So actually, first let's simplify H a bit more. And for that, what we're going to do is have 1/, this thing. And that's a 1 now. And then we're going to want to factor out a 21. So we're also going to have a 21 over there if we do that. Okay, now the reason you want to write it like this is because now we've got 1/21 times the root of 1 plus this whole thing squared. And at the 3 dB frequencies, we're going to need this to be 1/21 times √2. So So at the 3 dB frequencies, what we need is that this bracket term here is equal to 1 or -1. The way to get this thing in brackets under the root to be a root 2 is to have this second term to be 1 or -1. And that's going to make this a little bit easier to solve. So then we're ending up with a 1000 over 21. And we could sort of just check that just see what the units are doing right now. Maybe before we mess with stuff, we'll simplify this out a bit. So we've got a kilo ohm there, and if we were to bring the ohms into the denominator of the denominator, we've got henries per ohm, and we've got ohm farads there. So a henry per ohm is itself a second, because think back to your LC, your L over R time constant from transients, and same thing with an RC time constant. So this is in seconds as well. So you could kind of factor out the seconds from the denominator here and the numerator. So if we multiply numerator and denominator by seconds, then every ohm will end up multiplied by seconds, which is what's going to cancel out the rads per second units that it normally has. So then everything's consistent from a unit perspective. Great. Okay, so that's good. Last part then, we're going to cross multiply by this, and then that's the same as having a plus or minus on the other side. So we've got 1000 over 21 times omega times seconds. And then on this side, we've got a omega times seconds squared times 0.1 minus 1e6. Okay, so then we can use the quadratic formula after we move stuff over yet again. So we're going to have this thing, 0 equals this, maybe now plus or minus again, 1000. Oh, actually, when we move it over here, it would have just been plus or minus. So now we've got a, now we really do have a minus plus there. As we put that on the same side. And so here we can jump to quadratic formula. So that means omega s is equal to negative b, so that would be plus or minus again, 1000 over 21. Now a separate plus or minus, not to be confused with the first one, root of b squared, 1000 over 21, minus 4 times a, 0.1, times c, 1e6, divided by 2a, 0.2. Dividing by 0.2 is like multiplying by 5, so we can clean that part up from the denominator. So we've got like a 5,000 there and a 5 there. And then under the root, we've got a 0.4 e6. Oh, and actually, this term was negative, so really this gives us a minus this times negative that, and that means we've got a plus. Okay, so we could even square this term if we like. So that's going to give us another 1e6, and we're going to be dividing by 21 squared. So, aha, now this term is 1 over 21 times the 5 with 1000. We could take the 1e6s out, and they become a 5000 as well. And so you see that we have this term being always bigger than this term, which means the only way we're going to get positive answers is if we use the plus sign there. So maybe we'll make a note about what we did there. Need the positive root for positive answers for frequency. So if we've done everything right, then we've got this term plus or minus this term, which means that this should end up being the center frequency, and these terms should be the difference from there to the edges of the bands. So let's check. 5,000 times the square root of 1 over 21 squared plus 0.4, and there is actually something really close to the answer that we were expecting to be the central one, but not exactly the same, not completely perfect. And then from there to the bands, we've got 5,000 over 21, which in decimals is 238. So you could rewrite this thing as the 3 dB frequencies are equal to, let's see, 3171 plus or minus 238, which would equal how about we do it like this? $29.33 rad per second and 3409 rad per second. In hertz, we end up with 543 hertz and 466.8. So let's say 467 hertz. All right. So that is so the term here is not quite the center. It's maybe it's the center. So what we found here is the center in linear space, but the actual resonance is going to be the center in log space. So if the bandwidth is kind of large, then you're going to expect that the term in the center in linear space can be significantly different from the center in log space. So that's why we ended up with 5163 rads up there, but this one ended up being, 3163 rads, while this one is 3171. So it's a little bit different. So what we did is we looked at this circuit, we analyzed it by inspection by saying, oh, okay, an L and a C in series are going to have zero impedance at resonance, and that's going to cause this to have no gain, whereas at the extremes of frequencies, this is going to act like an open, so we are going to have some gain, but because we've got a 50 ohm from the two resistors and then a 1K up there, we expect a non-unitary gain. So we expect gain to be lower than 1, and in fact it's 1 over 21. Okay, then we calculated the 3 dB frequencies after we found the central frequency. Central frequency would be the notch for this one. So in that case, that's a minimum gain. It's where we have the L and the C balancing and canceling out their impedance. And then the 3 dB frequencies would be where the gain drops to 1 over root 2 of the maximum gain, which in this case is the gains at the extremes. So let's check out whether or not these 3 dB frequencies are the same as the ones that we get in the simulation of the circuit. So here is this circuit drawn out, and we'll put in our Bode plotter tool here, setting up our input and output. And let's see what we get. So we see a notch somewhere in the middle. We expect it to be around 500 hertz. So let's just zoom in to that. Seems pretty good. You can type in stuff if you don't want to have the, if you want to scale it a little bit more precisely. So let's go 400 to we could even go 550 and see how accurate we get. Okay, and then we'll scale up this. All right, so let's see what we have here. We've got the notch getting us down to pretty low, so minus 51 decibels. That's quite some attenuation there. At the ends, on this scale, we have some pretty fair attenuation too. So I guess we need to go up a little bit higher in frequency. So at the extremes here, we've got an attenuation of minus 26.444 decibels. And where that comes from is we expected the gain in frequency to be the gain in amplitude to be 1 over 21. So if we do 20 times log 10 of 1 over 21, and maybe we'll force floating point arithmetic there, it's that negative 26.444. So that's the decibels that you would expect at the edges, which means that at the 3 dB frequencies, we are going to be 3 decibels lower than that, so 29.444. Let's see where we get close to that. So somewhere around here, and then if we look, that's at 466.6 hertz, and that's exactly what we calculated. Now on the other side, we've got, we're again looking for that 29.4 there. Oh, that's pretty good. And that's 543.6, which is also exactly what we calculated. So there you have it, 3 dB frequencies and resonant frequency calculated for a notch filter.